before the break, we took a look at how a CNN is put together, all the equations for the forward pass and the back propagation, right? Okay, so like I said, at least one time you have to program it, so your next assignment will be programming a CNN. And because this can be really a nightmare if you started on your own to build it, so that you can hopefully get it done in a week or two. I'll give you the code in C#. Let me quickly describe the code, 5-10 minutes. Then I'll talk about another advanced concept related to CNNs, okay, which is very popular these days. Okay, so the code that you will receive from me is in C#. Okay, and basically, okay, it's been a while I wrote this, but based on my memory. Okay, first let me show you how this was done. Okay. So the key idea was, if you take a look over here, right? This is where we are doing those convolutions. And if there were 4 feature maps over here, 6 feature maps over here, so how many convolutions we needed to do? 24, right? 4 by 6 type of convolution kernel array. Okay, same thing over here. In the beginning, you might say over here, okay, maybe this should be created differently from the second layer. So I wanted to create code in such a way so that we can create as many CNN layers as possible, very similar to our style that we did for the dense networks. Okay, so from that point of view, let's treat this also as there are 4 feature maps on the output side, there's 1 feature map, even the input, let's treat it as a feature map, so therefore we need 1 by 4. 2-dimensional array of kernels over here, right? So then basically what I did is I combined this part into a class called feature map. Okay, so if you take a look at one CNN layer, so if we create a class called CNN layers, how many layers are in the first, how many feature maps are in the first layer?
4 feature maps.
4. So basically then I can create a list of feature maps. Okay, and put it inside a CNN layer. So our CNN layer will contain a list of feature maps, right? So for example, it will have, this list will have this part, this part, this part. What's missing? So I have a list of 4 feature maps, right?
Mm-hmm.
What I'm missing over here are the kernels. So then this will have also a 2D array of kernels. Okay, so to summarize, the implementation will go like this. If we can write the code for one feature map class, okay, which is easy, right? What's a feature map class doing? It has some input, for example, 24 by 24 over here. Then what's this doing over here?
Summation,
Adding 1 value to all of these, right? Then it's applying an activation to all of these. Then whatever result we get, we are doing a subsampling. So the code to write this, if we sit down, hopefully we can do it within an hour. Create this class. Okay. Once this class is created, then like I said, what we'll do is we'll create a class called CNN layer. And as I mentioned a minute ago, what kind of data we will have inside this class? Okay, a list of
feature maps,
and what else?
kernels,
2D array of
2D
kernels. Okay, how will we decide what will be the dimensions of this array? We will need to know what
the input.
number of feature maps in the output, number of feature maps on the input, and then it will create that array, the array, right? Okay, so this way, is the second layer any different from the first layer? No, it's exactly the same. So then the whole network, okay, remember previously when we created our network class, if you recall, this was a list of
layers.
Okay, so dense layer, right? But now what will our network consist of? It will still be a list of layers because this is part of it. What else? List of CNN layers. So this class that we have created as a CNN layer will also be a list of. So both of these lists will be passed to the constructor of the network, and then of course the back propagation, as you can see, will be pretty challenging over here. So this is where all of our rotations and so on. So when I built it some time ago, okay, after looking at the picture and deciding this is how we should put it together, right? We need some support functions. Because if we have already clarified the operations that we want to get done, then it's very easy, okay? Since I built it in C#, but Python is actually a lot easier. C# does not have built-in capability to add matrices, multiply matrices, to do convolutions and so on. So basically what I did is I started with a class called matrix. Okay, those of you who have taken C++ would remember we can overload operators. Very similarly in C#, we can overload the plus operator, meaning we can define it so that it can add two matrices, it can multiply two matrices. What else will we need over here? Inner convolution, full convolution, right? We need a capability to be able to add a single element to all elements of the matrix, to apply activation to all elements of the matrix. So I spent a few hours in building this class so that this behaves very similar to NumPy. Once it is very similar to NumPy, then we can focus on our bigger goal of putting it together. So let me quickly show you the code. Once again, because you'll be using that code to put. Okay, so let's go to, let me start with the matrix class. Okay, and I'll be putting this code on the website if it's already not there. In the previous year's lectures, it should be there, but I'll put it in the, so let me start with the matrix class. Okay, so here's a matrix class. What kind of data it contains? Take a look, very easy. From here, can you see what data do we need? Can you guess what this is? Two-dimensional array of double decimals. And then how many rows, how many columns are there, right? And the constructor will simply create that memory. Okay, C# has two ways to declare two-dimensional arrays. One is like this, one is like this. These are called jagged arrays, and they execute faster. So instead of using the default array type. I use the jagged array type. Okay, let's take a look at what are the operations we need. Okay, sometimes we need transpose. So again, I wrote a function. If you're using NumPy, you already know np.t will already do it, so you don't have to do this, right? Then how do we add two matrices? Very similar to C++, do you see operator plus? So this way, if I declared a matrix M1, I wanted to just simply do M2, then this will automatically execute the code and be able to accomplish the addition, right? Same way, how do we multiply matrices? So I overloaded the star operator. How do we subtract matrices? Okay, as you can see from the comment, add in place. So when will we use it?
Add the bias.
Yeah, so for example, if we wanted to add the bias to each element of the 2D array, pretty easy, right? So I'm not sure why I put this another one, but okay. So very similarly, what if I wanted to multiply a number to each element of the matrix? Then if I have two matrices, okay, let's say 2, 3, 5, 6, 7, 8, 1, 2, 1, 4, 3, 7, right? What if I wanted 1 times 2? So I wanted
Dot product.
element by element multiplication. Yeah, similar to a dot product. So then this will be our code, except it doesn't do the summation, simply does an element by element multiplication. Then, remember when we are implementing CNN, right? Okay, let's say we applied a kernel. We got a 24 by 24. We added a bias. Then what do we do after we add a bias?
Apply the activation.
Apply an activation function, which could be, in the last layer, could be softmax or sigmoid. So I also made that a function of the matrix class so that if this is a matrix, I can simply do whatever this object is, dot softmax or dot sigmoid or whatever. So anyway, so that's basically softmax, then basically sigmoid, basically relu. Then here's the code for average pooling. Okay, then here's correlation. We don't need, okay, this was needed in some other things that I was doing, so I put the correlation also. Okay, here's the convolution code, and here's the convolution full code. Excuse me. So basically, when I built it, I used MATLAB to verify on some smaller matrices that indeed the code is correct. Otherwise, as you know, in software development, we should test it before you go to the next step. So, okay, this you don't need. This was for something else I was doing. Rotation by 90, flattening, clearing, cloning, copying. So anyway, now
Are we rotating on the forward pass as well?
are we?
Rotating the kernel on the forward pass as well?
No, not on the forward pass. The to answer your question, the answer is actually yes, but that's built into the convolution function. So the convolution function takes the matrix and the kernel and it rotates it before applying the convolution. So you're just calling the convolution. But if you, and the reason I said no was, in the backpropagation, if you recall, we had to rotate this first before we do a convolution over here. So in the forward pass, there's no explicit rotation. There is a convolution which does the rotation internally. But in the backward pass, rotation is first before applying the convolution. Okay, so anyway. Okay, so let me ask you this. Now, does this make sense? Can we build this extremely easy? What type of object is this? A matrix, right? And remember, we had an add function. We had a sigmoid, and then we had a subsampling function. I forgot what I called it. So this will literally be 4 lines of code to do the forward pass in a feature map, okay? Or 5 lines of code, okay? So anyway, let me now okay, just 2 more minutes, rest I will have you explore it yourself. Okay, if I take you to, let's say, a feature map. Okay, so this is the feature map class. And anyway, I have another enumeration called the activation type. So what kind of data will be storing the deltas and so on, and the bias gradients, and, right? Okay, so try to go through it. You'll be able to run it. It's pretty easy to run. So if you simply go, I made it for the same 1,000 data set. So I have a train button. You can save the train network. So sometimes you saw these attributes over here called serializable. Okay, and I'll show you later on how to save the train network in Python as well. Okay, but the serializable allows us later on, after we are done training, to save all the weights and biases, so that now we can test it on any input, right? So basically what will happen is, once it's done running, then I put a couple of buttons over here. You can load the train network, then you can pick a digit, any digit. So for example, over here, so, okay, maybe I haven't trained it yet, but anyway. So then you can test your code. So this code will be there. So please go through it. Now let me cover one more important concept, and so that we have something new for this week.
Professor, when we increase number of neurons, it could lead to overfitting. Here, if we increase number of kernels too much, could lead to overfitting.
Here, see, because those are learning features, so majority of the time, the more feature maps you have actually helps. Okay. I'll address this issue, like how many layers to put in. So basically with CNNs, okay, let's say we have a layer 1, layer 2, and so on, right? So for example, these days, people have created networks up to a few thousand layers. So imagine the training time it will take once you run this.
And number of parameters also.
Yeah. By the way, let me give you another suggestion. Okay. When you test the CNN, you will see as you program it, it will take a long time on your laptop. Okay. Laptops are not designed to run on 100% CPU for a few hours. Okay. So for example, last semester, one student who was doing his thesis was getting very good results, was very excited. So I said, okay, let's talk about the results tomorrow. He comes to me, says, Professor, my laptop fried. Okay, because he was running the CNN all night long to optimize few things that we were doing. So run it just 1 or 2 epochs, see if the loss is going down. Then I have set up the TensorFlow and the all the libraries that we need in one of the labs. I forgot it's 110 or something. I'll put it on the website. Those computers are decent, have good memory, so what I'll recommend is verify it on your own laptop, but if you have to run it for several hours, just go to one of the machines, run it, come back and collect the results, okay? So don't lose your laptop on training a network, okay? Okay, so, oh yeah. Was there a question I was answering? I forgot.
The overfitting.
Oh, overfitting, okay, okay, yeah. Okay, so we can have thousands of layers, right? So the common problem with CNNs is, as we put more layers, what happens is the gradients become very close to 0. Okay, so in other words, so you will see, oh, I put, let's say, 12 layers, and it's doing great results. You went to 15 layers, and all of a sudden the result went way, way down. Okay, it's because this is called the vanishing gradient problem. Okay. Because the gradients keep getting, remember the deltas are being multiplied, right? So, so there is a couple of very, very interesting concepts that I'll cover in the next lecture. These are called residual networks. Okay, then there are highway nets, and there are called dense nets. So they use a very simple technique to make sure that we can stack as many layers as we feel like it. So all of these where we have thousands of layers are typically one of these architectures. Okay, so short answer to your question now. Once we go into the details of this, then you'll see. Okay, so at least let me give you minutes. I have 10 minutes, roughly 15. Okay, let me at least give you the idea about the next topic. So one of the very, so like I was saying, CNNs lead to many, many neat architectures, more advanced architectures. So once you have an idea of how to create a CNN, right? So for example, one of the very important field these days is face recognition as an example, or recognition in general. Okay, so so let's say we create a CNN. Okay, we feed in some face. Okay, and its job is to recognize, let's take a look at our class. We have, let's say, 40 students. So its job is to classify one of the incoming faces as to who's the student, right? Okay, if we extend it to further, if we wanted to apply it to the whole university, so you go to the gym, some face recognition does an immediate recognition. So now let's pretend we have 5,000 students, so we need 5,000 classes over here, right? So those of you who are taking computer vision, we discussed a technique called PCA, which can be used for face recognition. But bottom line is, regardless you use a CNN, regardless you use a PCA, on a given data set, you may be able to get 97, 98% accuracy. But as soon as the lighting conditions change, the picture was taken somewhere else, it does a terrible job, okay? Including CNN. Okay, so what's the alternative over here? So fortunately, CNNs can achieve as good of an accuracy, if not better than a human, in some cases even better than a human. How? We create what are called Siamese networks. Okay, Siamese networks, what they do is they convert a recognition problem into a verification problem. Okay, so what is the verification? So this is what we do in a Siamese network. We put a CNN, we put another CNN. Okay, again, many layers over here. Many layers over here. And these two CNNs are identical in terms of weights and biases. Then what we do is we give it a picture of a person. So let's say person X. We don't know who that is. We feed it over here. Okay, we now pick a picture from our data set. So this is picture from data set. Okay, so let's pretend this is a picture of Bill, and if we have a picture of Bill stored in our database, then we'll feed to the second CNN. So this is CNN1, CNN2. Okay, remember in a CNN, our typical architecture is after we have a few CNN layers, then what do we do at the very end? We have a regular neural network, right? So what we do over here is, after the flattening part, so this is basically the flattened layer. We remove the classifier because we're not trying to classify. The goal over here in the verification is to compare whether two things are the same or not. Okay? So basically, again, so this is the flattened part, right? So as you can see, this will be basically a vector with some numbers. You guys agree? Vector with some numbers. Okay? Now we feed it to some kind of a loss function. And this basically tells us 0 or 1 essentially, or same or not the same. Okay, so now the question is, how do we train such a system? And by the way, this does a fantastic job. Okay, so you might be wondering, how do we recognize a person then? Let's say somebody walks in the door. It could be one of the 40 students. So then what will we do? We feed in one at a time, 40 pictures over here. Then this will tell us whether it matches to, if it matches to one of them, produces close to a low value, it's that person, otherwise it's not any of the recognized people, right? Okay, then later on I'll show you how we can further, it seems like terrible right now that you might say, what if we have 1 million people? Do we have to go 1 million at a time? Okay, there's a way to take care of that issue as well. But let's try to take a look at understanding how will we train this network, what kind of loss function will we use. And so we'll develop our very proper training backpropagation algorithm for such a case. Okay, and let me at least give you an idea, then next time I'll go into the details, and one of your assignments will be to actually implement this. Okay, so for verification, okay, one loss function that's very popular. Okay, that is popular is called contrastive loss. Okay, by the way, also from the same person who invented the CNN. So this paper also is very, very famous. I forgot, it has 5,000 citations or something. So anyway, the loss function looks like this. So essentially, let me first give you an intuitive idea. Okay, if you are given two vectors, right? How will you know they are similar or not? They're close to each other or not?
subtract both of them, the loss is equal to, is near to 0 or? if the loss is-
No
Euclidean
subtraction.
distance or correlation?
Yeah, Euclidean distance or correlation. Okay, so essentially what we can do is compute the distance between these two, like a Euclidean distance. Okay, suppose I call this dw, and we pass it through a loss function, and let's call this L as an example. So now let me show you the equation for the contrastive loss. Then if we know the equation for the contrastive loss, and let's pretend it's differentiable, okay, then can we do partial L over this? Suppose I call this output A1, suppose I call this output A2, the actual output. Can I do partial L over partial A1? Then will I know the delta over here? Then from this point on, what is it? Do we know how to train this if we know the delta here? Yeah, that one. We just went through the whole 2 lectures learning how to train the CNN network, right? So then it's same as regular, okay? Okay, so what does this contrastive loss look like? The equation goes like this. Half dw squared 1 minus y plus y max of 0 m minus dw squared. Okay, so let me see if this makes sense. Okay, so this basically takes care of if the 2 pictures we are feeding are similar. This takes care of the case when they are dissimilar. Okay, y is our expected output, just like before. Okay, so take a look over here. If y is 0, what will this become? Half dw squared, right? Okay, which essentially basically means minimize the distance between these two. Because remember, for a loss, do we try to make it bigger or we try to make it smaller?
Smaller.
Smaller. So the lower the dw, the lower will be the loss. So if both pictures were supposed to be the same, their distance should be smaller, right? So intuitively makes sense, right? In this particular case, this m is called the margin. So it's a constant, e.g. 2. So the idea over here is if they are dissimilar, then don't do the backpropagation if 2 images are widely different. Okay. In other words, what if I feed in a person and I feed in a tree? Then the distance will be very large, right? Why should we backpropagate on a large distance where this doesn't even make sense? But if I am feeding, let's say, all the people in the data set, they're all persons, and then I know even if they are different, the maximum difference is 1.9. So then it would make sense to do the backpropagation for the different case. So that's the intuitive idea behind